Hello, everyone. Let's now turn to the second section, which I'm going to use one example to demonstrate the steps for the phase lead controller design. Um, let's take a look at this example here. So here for the open loop system that is given by here. And our goal is to design the phase lead controllers to meet the three performance indexes. One is the KV. This is based upon the steady state requirement. Here I'm going to demonstrate a little bit more in details. The second one is we wish the closed loop systems have a phase margin is larger than 50 degrees. And to say so, we have to know what is the phase margin for the open loop system, and we're going to do it quickly. And the third one, gain margin of the closed loop system hopefully is larger than 10 decibels. Based upon the three performances, the performance indices, we would like to determine the three parameters and such that the controller can be determined. Okay, now we back to our step one. This is the characteristic equation for these closed loop systems, and based upon which we can also know the error. Okay, the first one, we determine this one by meeting the steady state requirement. And here, if you remember, this is our ES. And for example, this is R, this is C. So ES equal to R minus C. Okay, the steady state error, if you remember, that is limit as approaching to 0 S times ES. Okay, and for the steady state error, for the closed loop function, basically that is GC G 1 plus GC G. So in this way, you should be able to formulate E equal to, I'll leave that for you, okay? So from there, you can proceed to do this one, and then after the few steps later on, you should have this term appears, okay? And have this term appear subject to, I would guess, is the unit step input, okay? Okay, now for this one, simply we focus our exercise on this term here. So for these terms, we are given the GS, which is this one here, and we know the template of the controller that is here. So by executing these conditions, then we can find, and that result will be this one. And this one, by meeting the requirement, this is a given performance 20. So we formulate this as our first equation. Okay, Kc alpha equal to 10. Now, go to the second steps. So with that one ready, so 10 multiplied with GS, and which is numerator is 4. So that is our gain adjusted. The whole terms, again, in our textbook, is called the gain adjusted open system, GS. Okay, that is this one. Now we look into the body plot to find out for these open systems, what is the phase margins. Okay, so by performing, either you can draw it by hand or using MATLAB. So that is the one here. You can see this is our phase margin. That is a magnitude I highlight here, and that is about 9 degrees. And that one happened at omega equal to about 63 radians per second. This plot, you can use MATLAB in this command here. Okay, so definitely here, this is about 9 degrees. And again, our requirement is we wish to have a 50 degrees. So from here, you can see the discrepancies between 50 and 9. That's a 41 degrees. So here, that is our desired number we wish to achieve, which means from here, theta is 41 degrees. That simply is a discrepancy between this and the desired. Now with this information ready, we move on to the step 3. Step 3, again, the focus is to determine what is this number. Okay, so once we have this one determined from the previous slides already, and then we plus certain flexibility. So here I pick 5 degrees. So that means I determined my VM is 46 degrees. With that number ready, I can calculate alpha. So alpha equal to this one. So that is our second equations. Okay. Again, our first equations is this one. Okay. How many parameters? Again, 1, 2, 3. So we need one equations. Second equation, we need one more. The here I like to make note. If you like, you can also choose, for example, 10 degrees. Okay. So basically, there's a flexibility here, but also this will make these questions open. What I mean is there's no unique solutions for this kind of design questions here. Okay, we move on to the next steps to look for the third equation for our problem. Now for the step 4, we like to determine the this one. This called the gain crossover frequencies. And how to determine this? From this body plot of gain adjusted GS, which is open systems, you simply looking for a particular frequency at which the magnitude, I would say at which the magnitude equal to negative numbers of what numbers is this number. So again, in this step, you have to first determine what is H. H is based upon alpha. Alpha is previously determined here. Okay, so you have alpha in place. You can determine H, which is 17.6 decibel. So with this number ready, you simply scan through the body plot of the open loop system such that this magnitude is negative H. Okay, you're looking for at which frequency, we call the WCG gain crossover frequencies, at which the magnitude on the body plot of open loop systems is minus H. Okay, so you have the minus H, which is minus 17.6. So you simply scan through and look for this number. This one, you need a little bit rigorous to do it. So here is the MATLAB code I made for you. Okay, but roughly by our bare eyes, you can estimate, if you put the scales carefully, minus 17 is about here in this range. Oops. Okay, about in this range, that one has minus 17. So here, we're searching for the range I search for the range between 8 and 12. And then by looking for that one, I can precisely determine omega G actually is here. Very close is here. Okay, omega G. By doing so, then we have omega G be ready. So the last step is with omega G, we can determine omega G basically can be correlated to that formula. Oops. Here, okay, omega G is equal to this one. So from here, we can determine T. So that is our third equations. With 1, 2, 3 equations, we are able to solve for T, Kc, and alpha. Alpha has been solved in, I think, step 3. So that is our controller design. And you can follow up our textbook. This example is from our textbook. And however, I believe solutions in this example in our textbook has a little typo. So the numbers showing here is different from the numbers in our textbook. But anyhow, you can verify it. That is the steps. Okay, thank you.